Um, Now, so that's, that finishes this discussion of black holes. And so now we are going to consider slightly different application of this, which is the application of using this holography to learn about strongly interacting theory. So imagine that you don't care anything about gravity. So I'm a physicist that does not care about gravity. I'm interested in, let's say, nuclear physics. Okay, I'm interested in so nuclear physics is described by quarks and gluons that are themselves strongly interacting particles. They live in 4 dimensions. And so we've seen that this correspondence relates a system of strongly interacting particles to some system in higher dimensions. So you can imagine that you have these gluons, and then they describe in an alternative gravity theory, but now in 5 dimensions. And you can use that 5-dimensional theory, that 5-dimensional universe, to calculate some properties of those particles. And in this way, we can get some information out of black holes, but in a different sense, that we use black holes to get information about strongly coupled systems. So in this way, suppose you are interested in collisions of heavy ions that produce a new state of matter. It's called a quark-gluon plasma, but it's more like a quark-gluon fluid, where you create strongly interacting quarks and gluons. And so you can view this as creating a new phase of matter, or you can view it as creating a weird a black hole in a weird 5-dimensional space. And in this way, you can analyze the system, and by thinking about this, people have found very interesting relationships between black hole horizons and hydrodynamics. And in fact, Loganayagam, who's a professor here, has been doing excellent work in this direction of understanding the relationship between horizons and hydrodynamics. Now, another connection that is also related to what we were discussing when we talked about the analogy, the verbal analogy, is a connection between entanglement and geometry. So entanglement is a quantum property of, well, an eminently quantum property of nature, and it in this correspondence, it plays an important role in creating the space-time geometry. And we'll discuss just one example of this, just one simple example. There are many other examples that support this point. And we'll go back to this solution that Schwarzschild found. And as I said, it's a confusing solution, and it took a long time to understand. And it took about 50 years to understand. And so the final person who really understood it thought about the solution in the following way. So this is a small diagrammatic representation of the solution, where the vertical direction is roughly time, and this horizontal direction is roughly like the radial direction. And on each point on this diagram, there is a 2-dimensional sphere that I'm not showing, and it's not important for what I'm going to say. Well, it's somewhat important. The important point is that this whole region, this whole right wedge here, represents the black hole exterior. It's what we saw in the very beginning. It's the region outside the horizon. Then there is the region inside the horizon, the region that was looking like a collapsing universe. This black line here corresponds to the region where the space-time curvature becomes infinite, or the singularity. And the full solution contains actually a second region, which is another exterior. So this also looks like the exterior of a black hole, and this also looks like a horizon. And so this geometry looks like 2 black holes joined that are sharing a single interior. So these are 2 black holes that could be living very far away and are sharing a single interior. So that's the actual original solution of Schwarzschild, has this form. Now, collapsing black holes are not exactly given by this, because they are made with matter, and this is a vacuum solution without any matter. So collapsing black holes are only a portion of this geometry. But if you look at the original geometry that Schwarzschild found, it has this particular shape. And we can interpret it as a kind of wormhole. So we can imagine that we have 2 black holes that are far away, and they are sharing a horizon. So these black holes could be, let's say, one is here, one is 1 million light years away. But if you are 1 meter away from this black hole, and your friend is 1 meter away from that black hole, They are separated by 1,000,000 miles in the 1,000,000 light years in the ambient space, but they could be just 2 meters away through the interior. Now, as I said, if you find two black holes in nature produced by natural gravitational collapse, they will not be described by this geometry. So these are some very special black holes. I'm not going to tell you how one could produce them, but let's say that you could find such a configuration. This is one important point is this kind of wormhole that exists as a solution of Einstein's theory is not the type of wormhole that you see in science fiction movies. Okay? So wormholes in science fiction movies allow you to go into some region of space and then emerge far away almost instantly. This is not of this kind. In fact, those type of wormholes, of the science fiction wormholes, I think don't exist, cannot exist, and in fact, there are some, using Einstein's equations and reasonable properties of matter, you can show that they don't exist. But these are different. Here, as I said before, if you have a person here sitting 1 meter away from one and 1 meter away from the other, they are separated by 2 meters. But if these wormholes are a full space-time geometry, and they are dynamical, so they are 2 meters away, but it's an evolving geometry, and as time evolves, these two observers are separating. So this wormhole is stretching along this radial direction, is becoming longer as time progresses. And also this two-sphere that we were talking about is shrinking as we approach here. So if an observer wanted to go from here to the left, it can only move at the speed of light, and the speed of light here is represented by a 45-degree line. So it cannot ever move across this horizon here. So if it starts from this side, will fall to the singularity and die at the singularity, but will not be able to go to the other side. So there is no signal from one to the other, and also no causality violations. You cannot travel faster than light in the ambient space using these wormholes. And these are consistent with the laws of physics as we know them. In fact, they are the simplest solution of general relativity. Now, the idea is that in the exact theory, we've been arguing that a black hole, as seen from the outside, is described by a set of microstates. The black hole is more or less like an ordinary quantum system that has a certain number of states, of quantum states. And so each of these black holes would be described by a set of microstates. And as any other quantum system, we can consider them in an entangled state. So we can entangle the states here with the states there. Entanglement is a kind of correlation. A kind of correlation somewhat similar to classical correlations, but a little stronger than classical correlations. And the idea is that if you were to correlate them in this way, in this entangled state, in a particular entangled state, then we would have the wormhole, and we have this geometric connection appearing in space-time. So from the outside, you see the same two black holes, but when you go in, you see that entanglement creates a new space-time that connects the two black holes. So the reason I told you this is because you see that the space-time geometry depends on the entanglement between the two. Now, these words might sound a little weird, so let me just go back to the verbal analogy and try to explain what this means in the context of this analogy. So here we have the same sentence that we had before, and here I put a Spanish translation of the same sentence. Okay. Now, when you start analyzing this sentence, of course, the details of how you form the words are different in Spanish and English, right? So which letters give to which words are different. But the structure of the sentence is the same in both cases. So when you start analyzing the sentence, at some point, the two structures become equal and are perfectly correlated. Okay? And so so in that sense, if we did some analysis like this, you would have a shape roughly like this. So here, at short distances, you have different structures in the two sentences, but there is some common thing that is common to both sentences. And so in this case, we can say that that's a wormhole that connects the two sentences. Now let me explain what it means what this entangled state means in a kind of little nice story. So this is a kind of science fiction story that you can make with these wormholes. And so this is one way in which you can use these wormholes. So imagine that we have two people, let's say Romeo and Juliet, and their families don't like, well, they like each other, but their families don't want them to be together. And so they confine Romeo to this galaxy and Juliet to the next galaxy. Now, this is sometime in the future, and these two are very, very smart, and they start exchanging messages and so on, and they arrange to form two perfectly entangled black holes. Okay? And once they make their own black holes, they do the following. So here is Romeo's black hole, and here is Juliet's black hole, and Romeo is standing outside his black hole, Juliet is standing outside her black hole, and this is the full space-time geometry of these black holes. Okay? Then they jump inside their respective black holes, and so their families just see them jumping into a black hole, and they think they committed suicide. Okay? And the writer of the story also thinks the same thing and writes that. But secretly, what happens is different. Let's now look at the top figure. So Romeo and Juliet go in, and they meet inside the black hole, and well, eventually, in this version of the story, they just die at the singularity. Okay? Now there are some other versions of the story where we can extract them from the black hole by doing some more complicated process, and actually manage to transfer Romeo from one to the other. But I'll discuss it. That's a little bit more complicated. One question that we don't understand is if we describe the black hole in terms of this description far away, where we can see all the microstates clearly, we don't understand how to describe the interior. So the equivalence principle tells us that the horizon is nothing special, and there is no problem when crossing the horizon, but we cannot describe the interior using the same variables that make quantum mechanics manifest for the outside observer. So we don't know yet how to do that. Some interesting work in this direction was also done by Subrat Raju and Kyriakos. Subrat Raju is a permanent faculty here at ICTS, and Kyriakos was Papadodimas is here and was participating of this workshop. They proposed some interesting way to do this, but we don't yet understand all the details. Now, in conclusions, black holes are fascinating objects where the geometry of spacetime is deformed in a dramatic way. Black holes and quantum mechanics give rise to interesting theoretical challenges. String theory can describe black holes in a consistent way, at least seen from the outside. And spacetime seems to be an effective concept which arises from more elementary particles living far away at the boundary of spacetime. And entanglement of these particles that live far away plays an important role in determining the geometry of spacetime. Well, thank you.